So we're looking at week 16, third one down. We have an assignment called balanced and unbalanced forces. We're going to be looking at balanced and unbalanced forces and to see what it does to cause acceleration. Okay, so click on that link so it will take you to this. Okay, well, we're going to be working through it. Okay, so put your name at the top just to make sure that in case you lose it, that it will find your way back to you. Okay, we right now are going to be using this simulator to help us answer some of these questions. Now it tells you pretty much right at the top, it says net force section. So we don't need to be on the motion or friction or acceleration. We need to be on this first one, the net force section. Okay, and so this, follow along on the handout, participate in the discussion, and I think you guys are going to learn a lot. So net force section, we are going to be enabling some measurement functions by checking boxes in the top corner. So I have to click on net force section, and I'm going to select all of these: sum of forces, and values, and speed. That's what it tells us to do. Okay, number 1 says explore the program by placing blue and red figures on the rope to simulate a tug of war. So let's go with like this guy on the, he's going to be near the end but not at the very end. And I'm going to go with like a little guy that's going to try to pull from like, you think you should pull from the front or from the back?
Yeah.
Front? Who do you think's going to win?
The little guy.
The big one.
Why do you say the little guy?
Size. The little guy can be strong. The little guy
Okay,
can be
but
fast.
the little guy, it tells us that the force the little guy is able to provide is 50 newtons.
Oh,
This direction. And the blue guy, the big guy, is 150 newtons.
The big guy.
And the net force is in the blue guy's direction. He's able to tug with like 3 times as much.
Oh wow.
Oh, that's so sad.
Poor guy.
He
Poor
can
guy.
drive. That's tough.
So how could I actually get it so that the red side wouldn't be like pulled
Put 2
together?
little guys.
No, put the medium
Put
down.
the medium.
Oh,
Put the medium one back?
Yeah. Oh, they're no wait, what?
They're equal.
Oh wait, it's even. It's
Oh, yeah, that was- yeah,
So
that
a medium and a small,
Move it back one.
you know, the together they equal this guy.
Yeah.
It doesn't matter.
So if I go,
Oh.
no,
They make you strong.
they're like this for forever.
It's okay, guys. I mean,
You try
Okay.
placing the.
What if we
try
So
placing the little one in
which
the-
figure, 1A, which figure can pull with the most force?
The blue dude.
blue.
It's not just blue.
Boy.
Well,
Like I could put this one over here
And it's the same.
and it's the same.
oh,
But this one is 150. This guy's 100,
that one's 50.
and this one's 50. So 50, 100, 150. So the one that can pull with the most force is the largest, the largest person. Okay, the largest person is able to pull with the most force. What is the exact measurement that each of these figures can pull? Well, we already talked about that. Small was 50. Medium guy, 100. Is it important to include the units? Yes. Please write the units, which is just a capital N. It's important to have a capital N because that is the unit. You don't put it as lowercase.
Because it means something.
Yeah, it would mean
different.
something different. Okay? So we have one, the largest person pulls with the most force. They pull with 50 newtons, 100 newtons, and 150 newtons. So then they gave us an experiment. It says, place 2 small blue figures on the left and place 1 medium red figure on the right. It says, what is the resulting motion or speed? How much motion do you think there's going to be when I say go?
Oh.
None.
None.
Yeah.
There is no motion, 0 speed. Okay, so 2A, there's no motion, there is 0 speed. What is the sum of the forces? Well, the net force here, they show us is 0. Because my force to the left is equaling my force to the right. You know, thankfully we're pulling on a rope, we're not pulling on a person or pulling on taffy because we pull it right apart. He says, use a math equation to show how the net force was calculated. Okay? What kind of equation could I use?
100 minus 100.
Okay, so,
Or 100.
or we could say the left force is in the negative direction, so we could say minus 100 newtons, and then add the positive on the right, plus 100 newtons equals 0 newtons. Or if I could also say 100 newtons, subtract 100 newtons is equal to 0. I would accept either of those. The important thing is to know that one of them is going to be positive and one of them is going to be negative. Because they're vectors. They have a direction. Direction is important to understand the net force. Are these forces balanced or unbalanced? How do you know?
Because there's no motion.
Because there's no motion, we know that it's balanced. So anything that is staying still has balanced forces. Are we ready for 3?
Yes.
David, are you writing anything down? Okay, just checking. Just checking because we're already on 3.
Yep, I'm on three.
What was that?
What was the speed?
What was the sum of the forces? That's this right here. Sum of the forces equals 0 newtons. Okay? Question 3. Now we need to place 2 small blue figures on the left and a large red guy on the right. You're already afraid?
Oh.
Okay.
What kind of motion do you expect?
That right. Well.
Do you expect it to move towards the red guy?
Yes.
Okay. So do you think that there's gonna be motion?
Yes.
Yes.
What kind of speed do you think there's gonna be?
Like, slow speed.
Kind of a slow speed?
Oh.
Oh, it's
Oh. Oh.
Just a slow speed.
Oh. Oh. Oh.
Now, did you notice anything about this speed? Watch. It starts at 0.
And then it's speed.
Well, watch what happens. Tell me if this is a constant or a changing velocity.
Changing velocity.
It's a changing velocity. It's constantly speeding up. So the resulting motion is that we have motion towards the red side. We actually have the blue guys, or actually all the guys, speeding up. They're actually moving with more increasing speed.
So for A, we say increasing speed? Or
You could say increasing speed, and it's going to be increasing speed to the right. So what's the sum of the forces there? Sum of the forces they show us here, sum of the
50.
forces equals 50 newtons. We need to show a math equation again. Okay? We could say that 150 newtons
150
Subtract.
minus
100 newtons
100,
equals
50.
50 newtons.
So.
150
Oh.
newtons subtract 100 newtons. If I wanted to do it left then right, I could say negative 100 newtons plus 150 newtons equals my sum, which is 50 newtons. Are these forces balanced or unbalanced?
Unbalanced.
Unbalanced.
Because
You don't really have much room there, I'm sorry. That kind of went weird on us. We know because there's movement. You could say unbalanced,
Movement.
there's movement. Okay? So what happens to this cart when one side is winning the tug of war?
It moved. Well,
The speed
it
is-
the speed is changing.
The speed is changing, it is increasing. The speed is changing and increasing when one side is winning. Okay? Is this type of motion considered acceleration?
Yes.
Yes.
Why?
Because the speed is slowly
Change.
increasing.
Well, the speed is changing.
The speed
It's
is
going
changing.
up.
The direction isn't changing. Okay, the people are still facing the same direction, but they are accelerating because the speed is changing. Okay. What happens to the speed of the cart when the tug of war is a tie? Well,
It doesn't.
It doesn't
It
move.
doesn't move.
It doesn't move.
There's no motion or speed.
So if the tug of war is a tie,
It would just stay.
It will be a
so you say that in this case, the speed of the cart remains the same, the speed of the
Yeah.
cart remains 0. Would you consider this acceleration?
No.
No.
Because acceleration is what?
Acceleration is when it's moving.
Slowing up.
It is gonna be
Slowing down.
changing the speed or changing direction. We have neither happening. So we have no acceleration, we have 0 acceleration. Okay, see if you can answer 6 for me. If I have 2 figures pulling in the same direction, what happens with their individual forces? The individual forces do what? Like if I just have one, like one of these is 50. I had a second one in the same direction, what happened? They
It-
add together. If I add another guy, adds together, add another guy, adds together. But this is the maximum force that can be applied to the side. So 6, when 2 small figures are pulling in the same direction, their individual forces are adding together. Now if I have 2 on opposite sides, what happens?
They're all subtracting.
They subtract from each other. So when they pull in opposite directions, their individual forces subtract. Okay, an unbalanced force is when the sum of all forces is what?
Is
Inconsistent.
No.
Well,
For it to be unbalanced, what do I expect to see in the sum of forces?
Oh,
the
it
whole
increases.
amount.
An amount?
The amount
the amount going like either way?
Like would I expect movement on this one?
Yes.
Yes.
Okay, so this one's 50 newtons. Would I expect movement on this one?
Yes.
Yes, because it's 50 newtons the other way. Would I expect movement on this one?
No.
Why?
Because they're both.
What happened to the sum of forces?
It's zero.
Is zero.
It's 0. So an unbalanced force is when the sum of all forces is
Zero.
not
Oh.
unbalanced, not 0,
Oh.
and causes the object to, if those forces are not balanced, and we have something that's not 0, what will it cause the object to do?
Move.
Move.
Yeah.
Now, if I do have balance forces, then the sum of all forces is 0. Okay, make sure you're writing all of this down. And it does not cause the object to
Move.
move.
So it's
So 8, sum of all forces is not 0, causes the object to move. 9, sum of all forces is 0, and does not cause the object to move. It all makes sense, doesn't it?
Yeah.
But it's another thing to actually see it, rather than just talk about it. Okay? So now we need to go to the friction section. So we're going to look for the friction section underneath. I see that right here. Okay, so we have a box that we can apply some force to. So if I start pushing, you notice that if I start pushing, I start applying a force. But what do you see for those arrows? What's happening?
The leg is
There's also this other force that's always acting in opposition to the movement, and the force that's applied, that's the friction. And friction usually it tends to be smaller. So I can start to push, and it will move, and if I stop, it slows down because of that friction. Okay? So as we need to set our friction to medium, so that's where we're at, friction set at medium. That's this on the top right. There's forces, sum of forces, values, masses, speed, and friction. Okay? So friction, that little slide is in the middle. Okay? We need to select just one crate, that's what we have. This one is 50 kilograms. And we're going to apply a force to the right using just a single arrow button. So we're going to click. So 1, doesn't really do anything. 2, 3, 4, 5, 6, 7, 8, still not seeing any movement. 9, 10. Uh-oh. Uh-oh. Did we break it?
No.
No.
Maybe.
What is the friction force? The friction right now is matching. Because friction and the force that we're applying are matching, this is the static friction. So our friction is actually 10 newtons. Because the friction and the force that we apply match, we have balanced forces. We don't have any movement. Right?
So your friction force.
Friction force here is 10 newtons. We have balanced forces between the 10 newtons that we apply and the 10 newtons of friction that the box won't move. This is static friction. What is the sum of the forces right now?
Is some of
Zero.
the force.
Zero. In which direction?
To the.
It doesn't-
It doesn't matter, it's 0. 0 newtons. Is this crate accelerating?
No.
No.
Definitely not. It is not moving. There is no acceleration. Okay. So, let us increase to 100 newtons. See if I can do it here. How much is this add? Ooh, that gives me 60. That's too much. I'm just gonna go all the way back down to, see if I can go all the way down. Oh, it won't let me. I'm gonna go to here. Back to 0. And I'm gonna bring, I'm gonna go there. There we go. Okay. So I need to apply 100 newtons. I'm gonna go all the way up to 100 newtons. We should be moving. Why is it not moving for us? It should be moving. I'm gonna reset this just because I'm not sure if something's going quite right here. This is just a 50 kilogram crate, right?
Yeah, wait, I think so. It is.
It is, okay, just checking. We have medium friction.
Oh, it still
We're gonna
doesn't move.
push with 100.
What is it?
I would have expected it would have moved by now.
Nope.
It moves at 200.
So, at this point,
It said 100 newtons. Some of us is new.
I can get it to 100. I'm surprised by this. I would have thought that this would have actually been able to move, but it's still not. It says, what's the friction force?
Is it? I mean, yeah. wait,
Friction
yeah,
force
friction
is-
100.
Still 100. Even though the applied force is 100, they're equal to each other. Sum of the forces
Zero.
is 0. We have 0 net force.
No direction.
Not moving. It is not accelerating in any direction. Okay, let's try 200.
Okay.
Nope. Try that again. 200. We finally have movements. What's the friction force? Can you read it?
94.
94 newtons. So here in part C, the friction force is 94 newtons. What is the sum of the forces?
94.
Unfortunately, we kind of let go. We might have to like go back.
No.
We're gonna have to reset.
Why you like that?
I don't know. I wasn't watching.
Yeah, I know.
So he's applying, and probably accelerated so much that he
It's
finally.
106.
We're going to click all these. So right now, I'm still seeing 104. Oh, sorry, we're looking at some
Yeah,
friction
it's-
force.
The friction force is 106.
94.
No, I don't think so.
Some of the forces.
I mean, the sum of the force is 106.
So if we're at 200, I'm gonna pause. Okay, at 200 newtons of applied force, the friction force here is 94. So C,
Yeah.
we're at
for
C,
one is 90.
step 1, what's the friction force? 94 newtons.
The sum of the forces.
Sum of the forces,
106.
Christian's definitely got that, 106. What direction is it going?
To the
To the right, or the positive direction. Is the crane accelerating?
Yes.
Yeah.
Yes, and in fact, if I just let it go, you see what happens?
It's still.
It starts accelerating so much that the person literally falls off. Watch.
It gets a split. It's taking over. There you go.
He has a phone.
He's like, oh, So let's move the applied force back down to 50. It's at below 50, but above 0. Okay, so we want it maybe somewhere in below 50,
What above?
but above 0.
49.
So I have it at 44. Okay. And if I do that, it's not letting me. Okay, if I press play, what happens?
It does not move.
We're back to not moving. How do you think I could get it to move with just that much force? Is there a way I could do it?
With help?
With
What's that thing?
What was that? Bella?
Actually, Texas said it.
Oh, it's Texas or
Look at the friction.
if I put less friction? Watch.
Do none.
It goes
We're
high.
reducing the friction, reducing the friction, reducing the
go
friction. Ooh, look at that.
I thought it was gonna go.
It's moving.
It's now moving. So even with the same force now, because the friction is so much less, it's able to finally overcome because I have a net force in the positive direction. Okay? So what happens when the frictional force is greater than the applied force?
It's
There's no movement. If there's too much friction, you can't move. Okay? Number 12. Compare the applied force to required to move a 50 kilogram crate.
Wait, what about?
Oh,
what
wait.
is number 8?
Number 11, what happens to the box where the frictional force is greater? We have no movement. If the frictional force is equal or greater to the applied force, we're not gonna have any movement.
Did we do B?
We did.
What was it?
We had no
friction was
movement again.
44.
We put the friction at 44 newtons. Sorry, not the, well, it was the applied force has moved to 44, and that still had a friction force of 44. So we had those balance forces and no movement once again. Are we ready for 12?
Yes.
Anyone need some help on anything before number 12?
Wait,
They missed one?
can you go through D one more time, please?
Yeah.
It's like all the way.
What is the friction force?
44
newtons. What is the sum of the forces? 0. Is the crate accelerating?
No.
No movement.
What was 11? 11 was because they didn't have
There's
no
no
movement.
Did you hear him?
Yes.
Okay.
Could you redo that one?
Review which one?
Redo the pushing. Press the repeat.
I'll just redo.
Oh, yeah.
Oh, you're good.
Yeah, pretty much.
I remember.
That's the problem with all of these is. So we applied 44, but the thing is we had to bring this down. So we went like this and we said, okay, we're gonna start at 44, but we reduced the friction until it moved. And this was really not on our sheet, this was just us going, well, what would it take in order for us to have movement? We had to lessen the friction in order to make that happen. Okay, so let's compare the applied force required to move this crate with the applied force to move something that's much more massive. So I'm gonna switch this back to the middle. I'm gonna just reset. Okay, so how much force does it take to get this 50 kilogram crate moving? Let's try pushing and find out. Tell me at what force does it start to move? So 13, definitely not.
Nope.
26, no.
All the way to 50.
Still not, still not, still not.
150. Right?
Still have no movement.
Wait.
It's gonna take way more than 100. Oh, I finally have some movement. So I start having movement.
And
95.
95.
No, okay, here's the
95
weird thing.
has movement.
Okay, I want you guys to pay attention to this. It's not on your sheet right now, but notice something. As I start pushing, I had to go way above 100. Okay? So watch, I'm gonna go way above 100. Like 110, still doesn't move. 116, still not moving. 123, still not moving. Okay, it took until like 129 before it started to move. And now look at the friction force. It's like dropped way lower. And even if I, like, where I had this friction force that was as high as like 106, now it's dropped down. What's with that? It's not a problem with this. It has to do with the types of friction.
Oh, maybe that's really like.
The first type of friction to get something moving is the static friction.
Yeah. And then,
And once I overcome the static friction, do we have wheels? No.
No.
So this is sliding friction. Sliding friction is less. So I've changed from the static friction to get it
Just
moving
like
to the sliding friction to keep it
keep
moving.
it.
So we went from well above 100, like 120 something, suddenly back down to 94. That's the two different types of friction. Okay? So we had to go to about 125 newtons. So for 12A, you can put like 125 newtons. Now, let's look at the refrigerator. How much do you think is going to be required for the refrigerator?
500.
Refrigerator, how much more massive is the refrigerator?
Is
Then we go to 200, so it's 4 times as heavy. Would we expect 4 times as much
Yes.
push? Or is it only twice as much? I don't know. Let's give it a try. So we're gonna start pushing this. Okay, we're at 80s, 100, 20, 140, 150, 60, 70, 80, 90.
200.
Woo! 271. Nope. 300s.
250.
Still nothing. Ugh. Do you think he's ever gonna move this refrigerator?
No, he's not gonna
No,
move
he
at
can't
all.
move it.
He's not that sure.
Urgh.
It's okay.
Urgh.
Well, I'm not that sure.
Ugh.
He couldn't push it.
It's okay.
Wow.
You might tip it over.
So, was he
Oh,
able to
if
move
you
it?
let the
No.
friction
He
less,
applied 500 newtons of
Wow.
force and still could not move it.
it's okay. He tried his best.
Now, think about this. Is the amount, originally it was like 125, I said?
129.
129?
Yeah.
Okay. Multiplied by 4.
129.
I wonder how close we were to moving it. Like, I'm thinking that we're close-ish. If we multiply 129 by 4, that's like 516, I think.
If you make
No.
the friction
Wait.
less,
Yeah,
it's
116. That's, oh, sorry. I know what I'm talking about. 516.
If you make the friction
If I make the friction less, yes, I definitely could move it, but I'd have to make the friction less of both.
yeah.
Okay, so how much more force is required to move something that has more mass? More mass needs more force.
Oh.
More mass needs more force. to move it.
So for.
So let's try putting this maybe like above here. And we'll go back to the crate. And we'll see, what does it take to move it this time?
Oh, okay, you're doing
We're trying to do it with less. So to move it, I don't need nearly as much force. This time it starts moving at like nearly 50 newtons or so. And then if I change to the refrigerator, and I try to move that,
Key charge. Oh, it's moving.
that's not moving yet. Oh, there we go, switch.
Oh.
Oh, we finally got something.
Oh yeah, he got it.
So we're up about 175,
So we're
Oh.
sitting.
right? So you can definitely see that there's a massive increase,
Yep.
okay? So let's compare the applied force to require a 50 kilogram crate when there's lots of friction, medium friction, no friction. We're on 13. So lots of friction. Ew. Can I move it?
No, whenever it has lots of friction.
Oh, no, I can. I can. It takes. That's 188, so it's gonna take about 190.
190.
At about 190, it seems to be a switchover.
Okay.
When there's lots of friction, it takes about 190. Now medium, we already had the medium. What was the medium?
129.
So about 129.
Yeah.
Let's go with none. Let's see what it takes. You ready?
Oh, yeah, he got it.
Like literally, like any force. It takes just like 1 Newton. You can sit there with no friction and just with your pinky, just move it across. Very, very slowly.
So with
Very
no friction, it would have been 1, right?
Yeah, with no friction, all I would have to do is like touch it and keep kind of like pushing at it. Like, you know, sometimes you do that with your friends, you're just like, and you can move mountains if there were no friction. And that's really it. Pretty cool, huh? So, play around with this. See what else you can learn. You can play around with anything else on the net force or friction simulations. If you want to, you can check out the acceleration and the motion ones. See if you can find any relationships that surprise you. Here's something. Can you guys tell me, okay, we also have people, like there's the refrigerator and the crates. Could you tell me how much the present weighs?
It weighs
10 kilos.
But can you determine a way to show me exactly how much it weighs?
Yes, you could measure it.
How? This is all we have.
Oh. Oh well.
So how can I
Put it up
tell
there.
what is happening with this?
by
the
so
If I replace the crate with the present, which we don't know what its mass is, can you tell me its mass? There are ways.
his mass is 94, right? Oh no, never mind. That's the friction.
Any ideas?
Maybe.
How much you put on?
Wait, what is
Okay,
it?
so how much I push on it will give us how much force is applied. So how's that gonna help me tell how much how much mass it has?
Compared to other objects.
Perfect. Compare it to the force needed for those other objects. So if I start applying a force here, not moving, not moving, not moving, still not, for middle friction,
go to 94.
I'm past it.
Oh.
It's
It's
moving.
Oh,
So
there it
it was like about 125.
goes. Okay.
So if it was about 125 newtons for that,
And
let's
for-
try this trash can.
Hey,
100 and, oh, that's still going.
Oh.
Okay, so that's too heavy.
Yeah. Try the little girl.
Try the girl.
Oh!
Forty.
oh,
You're gonna push your kid.
oh, that's not nice.
Oh my god.
That would hurt, bro.
She's not that hard.
Definitely
But
less.
it's
Oh,
still hard.
102.
So it's
Try to
more
click
than
so.
40, less than 100.
Try to crate.
Try the crate.
Place the crate on her
If
head.
it's 50.
100.
Oh, no. Oh,
200. It's 67.97.
huh?
Okay.
So, one.
Wait.
What do you think?
Zero.
I think it's like 55.
You
I
think
think it's
it's
60.
maybe close to 50,
Like,
but it's
close
close
to
more?
that.
It's close to
70.
Try the adult.
I
Try the adult?
Oh no. Oh, he's sitting down too.
Wouldn't you?
Oh, well, I did.
Oh,
you
that's
wanna
be
what
pushed
it's
over,
on.
No, that's definitely
No,
more.
that's too heavy.
He's heavy.
Definitely.
I think it's like
More.
60 or 55.
I'm saying 70
He's too
right now.
big.
You're saying 70? I think it is very close to the 50.
Yeah.
Oh, so like
It's gonna be
I think
maybe
it's like-
a little bit above the
yeah.
50.
Yeah. Because it started to move around the same
It moves
amount of
on.
minutes.
I guess.
Okay, so can you guys take pictures of your completed thing and turn them into Google Classroom? That's all I ask of you. We are. That was such a hard activity, wasn't
That was
it?
easy.
No, it was easier.
Did we
to
learn?
all the answers.
Yeah.
That was hard.
Hopefully we learned something out of it.
He,
Yes.
wait, hold on. I got this.
Like how to figure out how much something, how much mass something has just by comparing it
The other
to the other things. How much force was required to move it.
All the things.
We're like, that's spare
Can I
time.
break this thing?
Yes, actually. I got one.
I got it.
I mean, I didn't do the rest.
Not a lot of spare time, about like 3 minutes, but take pictures. Turn in those pictures, please.
You get it right.